I will speak about some results in computer-assisted mathematics. Because in many cases, I have no proof, but I have a lot of results composed by this maple. So I can show a lot of numbers and a lot of my hypotheses, but very small number of theorems. I shall consider some projective invariant of complex hypersurfaces. At first, this invariant was introduced in 17, and in fact, a simple version for plane curves is known from 19th century, though I will extend Blücher formula. And in fact, a plane curve is a special case of a hypersurface, though you can see some connection between very old results and new results. Так, что я должен сделать, чтобы был следующий слайд? Then I shall speak about the computation complexity. I shall use generalized register machines over a field of characteristic zero. In fact, it is usual to use the field of rational numbers, but in the general case, I can consider any field of characteristic zero. The machines was introduced in last century, and they are closely related to the machines defined by Bloom, Shoup, and Smale. But I have no relations greater in the signature of a field. And you can see K as non-ordered field. That is the generalized register machine. It contains infinitely many registers. Each register contains a number that is an element of the field K. If K is the field of complex numbers, we can replace complex number, for example, square of 2, in this register. And in one step, we can add or subtract or multiply such numbers. And of course, we have rational constants. We have only 0 and 1 in the signature, but in fact, we can construct any rational number machine has index registers. Index registers contains a natural number. And initially, the number of non-trivial registers, that is the length of the input. Initially, this number is placed in the 0th index register. The running time is said polynomial, then the total number of steps is polynomial in this number initially placed in the 0th index register. If we have a polynomial as an input, then its coefficients are placed into registers. A hypersurface in projective space is the vanishing locus of a form, only one form. A form is a homogeneous polynomial, and it is hard to recognize whether a given cubic hypersurface is smooth. But sometimes we can recognize non-smooth, that is, singular hypersurfaces in small dimensions. And we can recognize cubic hypersurfaces having reducible Hessian. For a smooth plane curve of order D, in accordance with well-known formula, they exactly d square minus d tangent straight lines passing through a point of the plane. You can see example when d equals 2, red circle, and two tangent straight lines passing through a point. For d equals 3, there are 6 tangent lines passing through a point. And contrariwise, if there exists maximal number of tangent straight lines passing through a point, then the plane curve is smooth. For singular quadric, we have only 2 straight lines. And in this case, from a point, we can draw a tangent straight lines. If we consider the 2 lines as a singular curve, then from a point passing no tangent line. But in this case, there are straight lines passing through a singular point. And I shall consider multidimensional generalization of this very old result. In multidimensional case, we have not a few tangent straight lines, but we have a corner that consists of tangent lines. In over the field of reals, this corner is a silhouette, and we can use the same name in general case, though I would like to define polynomial D that defines this corner, polynomial D that defines silhouette. For given integer n, let us consider square free form f in n plus 1 variables of degree d. Let us fix a point u. Every straight line passing through the point u consists of points with the homogeneous coordinates, and we can restrict the form f on this straight line. And let binary form R is this restriction of the form f. Then polynomial D that defines a silhouette is the discriminant of the binary form R. If x0 equals 1, in this case, we consider the affine space inside the ambient project space. Then the discriminant D is an inhomogeneous polynomial in coordinates x, and in the general case, its degree is d square minus d. Sometimes discriminant vanishes identically. If a straight line alpha is tangent to the hypersurface or passes through a singular point, then the discriminant vanishes. And if the point u is a singular point, then the discriminant for this point u vanishes identically. If you, so this polynomial is the desired polynomial. It defines the silhouette. In the general case, the polynomial D is inhomogeneous, but this construction can be defined correctly in projective space too. and it is crucial to prove that I have projective invariant. The set of all polynomials of type D, that is the set of polynomials of all silhouettes, generates a linear subspace that is called W, subspace inside the ambient space of all inhomogeneous polynomials. The dimension of the ambient linear space equals W. You can see how to compute W. And the first theorem, for every reducible form F, the dimension of the subspace W is projective invariant. If the form is reducible, then you cannot prove the same result, because if the form F contains a factor x0, then its degree is big, but its restriction on the affine space has small degree. Though we can prove this theorem if F is irreducible, or if the form F is reducible, but it has no hyperplane in the hyperplane at infinity as its irreducible component. The next theorem: if D equals 3 or more, and n is a sufficiently large number, then the dimension of the subspace W is less than W small. That is, W is a proper subspace in the ambient linear space. But in case of quadratic form F, in case D equals 2, the dimension of the subspace W equals the maximum number. Subspace W coincides with the ambient space. Next result. For given n and D, the dimension of the subspace W, considered as a function of coefficients of the form F, is lower semi-continuous. If we have a form F such that dimension of the subspace W is the maximum, then for almost every form of degree D, this equality holds true. And in fact, this equality holds for quadrics, and it holds for hypersurfaces in small dimensions. The dimension of the subspace W can be computed in polynomial time. In fact, to compute it, we need to compute a symbolic representation of the polynomial D, and coefficients of this expansion of the polynomial are basis of the subspace W. Though our computations are based on the computation of the rank of a matrix. There exists a polynomial time algorithm to compute the dimensions of a linear subspace. Это означает, что мне надо заканчивать?
Да.
Okay.
Ну, 2-3 минуты еще. Можно ускориться, пожалуйста?
You can see an example, and you can see some results. For binary form of the Fermat type, you can see that dimension of the subspace W is small. The ambient space is big, but the numbers in the last row are small. In fact, I have no time to compute the numbers for high dimensions, for high degrees. But I can suppose that the same is true forever. And in this case, you can see results about cubic forms of the Fermat type. In this case, I have computed a polynomial, and I guess this equation holds for all n. But in fact, I knew it is true only for small values. And another goes results for other cases. На самом деле я могу пропустить, а перейти к заключению, поскольку тут перечисляются мелкие детали. The computational results show that one can easily verify smoothness of almost every plane quartic curve, as well as almost every quartic surface in three-dimensional space by means of computing new invariant. The method also applicable to other plane curves. On the other hand, the same problem for cubic surfaces is hard enough because the proposed projective invariant is useless to recognize between smooth and singular cubic surface. But one can recognize singularities of some types. And we also compute our invariants and can recognize cubic hypersurfaces. This reducible Hessian in deterministic polynomial time. Thank you.
Your method is allow to recognize smoothness, but maybe it is in singular case. Maybe there exists such kind of approach to recognize the type of singularity, or not? Based on some invariant, maybe.
I can recognize some types of singularities. Not every, but some specific types.